So, hello everyone. I hope I am audible. Please confirm. Am I audible or not?
Yes, sir, you're audible.
Okay, thank you. And we okay. So let's start our discussion. Just a second. So let's start our discussion uh, where we are and till this point and what next. So so far we have learned about the language and how to build the circuits. Uh, Today, those circuits that we have built, namely the idea of entanglement, we focused deeply on the idea of entanglement and the four different Bell states. Uh, I hope everyone has at least tried to run it. That how we can develop a Bell state, and through that we achieve entanglement. So today, all those circuits, they will be doing some specific, will be seeing some specific things that no classical computer can match, and will try to see in an honest way that where is the advantage, where there is really some advantage and where it is hype. So with this, let's begin our discussion uh, of what needs to be discussed. First of all, that where we are. So we discussed entanglements, entangled qubits by hand. Yesterday we started with this whole idea only, and this entanglement circuit is actually now going to outperform the classical computation. So every algorithm that we will see today, specifically we will be going towards the Deuce-Joseph algorithm, Bernstein-Vazirani. These are proof of concept algorithms, as we say. Then the idea of Grover's algorithm and the Shor's algorithm. Uh, all of these algorithms will engineer interference in some way or another. So we will be arranging amplitudes so that uh, wrong answers cancel each other and the right ones are amplified. And we are going to start with two deliberately uh, contrived problems to first of all expose the mechanism cleanly, understand the basic idea, what exactly these algorithms actually mean, and how the quantum advantages, is there any quantum advantage actually, or it is just a gimmick. And then we'll move on to the idea of Grover and Shore, which everyone genuinely cares about. And we'll finish with the idea of what are the limits of all these algorithms, what are the current uh, trends and other limits. So this is the roadmap for today. Part A is all about why quantum algorithms are fast. That's the machinery, the starting machinery. Part B will be we will be discussing two exact algorithms that prove the mechanism, as it just discussed a while back. Part C is for the famous ones, that is Grover and Shore, and Part D is for the perspective and hands-on labs that if we feel that something it is getting a little bit you can say abstract, then this is deliberately done so that you can understand that how we can harness that these algorithms in when we move on to the actual hands-on. So this is the biggest idea, and we need to first understand that what are the misconceptions around different ideas that we have discussed till this point, whether it is superposition or interference, entanglement or measurement or anything like that. So the first misconception, and it is the biggest misconception, is that the quantum computer tries everything at once. This is the, you can say, the major misconception or the problem that everyone thinks that okay, if we are doing some quantum computing on whether it is a simulator or a quantum computer, we are going to try every possibility at once. This is not even the case. It is not even closer to what we are actually doing. So three specific ideas or three ingredients that we understand, they have to work together. And what are those? The first one is the superposition. That is, superposition will be exploring, will be used for exploring. Interference we use to select, that whether we want to select the particular answer, and we do not want to select some other answer. So superposition, what we are saying, it is exploring, and interference is selecting from those you can say explored options. And entanglement is acting on this whole space, the space that the superposition is selecting from, and the interference is superposition is exploring from, and interference is selecting from. And if we miss even any one of this idea, then there is no speed up. As simple as that. So superposition alone is kind of useless. That if we measure it, we will just get one random value. That is what we get in classical computing also. So superposition needs to be tied with interference and entanglement to give us the actual quantum. It moves us toward the idea of actual quantum advantage. So the main understanding in here is that the interference pattern is uh, the wheel. It is the major paradigm where it makes which answers are correct and which answers are wrong. It is the focus area with respect to all these three ideas. So I hope everyone is understanding the difference, misconception that has been lying around the idea of quantum computing. Now, to understand, to even start the idea of quantum algorithms, first of all, we need to understand a very basic idea, that is oracle or the query model. So all the early algorithm, or you can say most early algorithms, have been framed around a black box only. And this might seem odd, but let us try to justify that what exactly we are saying. That we are saying that everything is worked around a black box only. So what exactly is this idea? So we hand the algorithm a function it can call, and we simply count the calls. This is what quantum versus classical idea is, that we are just handing the algorithm a function it can call, and we are just going on to count the calls. Whatever the you can say calls are there, we will just count them. Now, why are we so much bothered about it? Because it isolates exactly where the advantage comes from. It means if we are asking the same function fewer questions, and instead of doing arithmetic faster, then that's a clean way to prove a speed up exists. So what we are saying, that instead of doing some arithmetic operations that can be like speed up, we are actually asking some fewer questions. Instead of maybe 100 questions, we are able to do our work in maybe 3 questions itself. So this whole idea itself will give us some is giving us some quantum advantage as we understand. And this is why the idea of this black box or the oracle is very, very important uh, from the get-go, from the first algorithm itself. When the first algorithm that we are going to discuss, Deuce algorithm or Deuce algorithm, this is the basic idea that we start with. So we can think of a kind of a counterfeit coin, that how do we find the fake in the fewest weighings, sorry. So if we have some counterfeit coin, let us say a 10 rupees coin, something like that, or a 5 rupees coin, how do we are going to identify? So we will be counting the weighings, that how many times it is like being weighed, and not the time that it is taking to weigh that. So the idea around this is that, assume that the oracle is given. We are right now at the starting assuming that the oracle is given, uh, although we are not knowing that what exactly resides inside that oracle, because as it is a black box, we will be just giving an input and we will be getting an output. But let us assume that the oracle is given. So for a real problem, the major idea is that building that oracle can be hard. For you can say a problem like traveling salesman problem, or a max cut problem, that is solved using Grover's algorithm. So if we max cut problem is very, very famous problem that is that is done through Grover's algorithm. So let us assume that we have to do some max cut problem. The major idea is not that how to solve max cut, it is to how to build the oracle for this max cut problem. And this is the hard part, and this involves a separate cost. So building the oracle in itself is a tedious task, and it is involving quite a bit of cost. In addition to that, when we will be performing the operation through that oracle, that is solving the max cut problem or any other problem, maybe traveling system problem or knapsack problem or any other problem, that again uses up some resources, whether it is the resources are with respect to time or space or anything. So what we are saying that, okay, as we can assume that oracle is given for some problems, for some starting problems, but for some real handling of the data, we need to build some oracle, and this oracle is quite tedious task to handle. So query speedups that we are saying, we just discussed that query speeding up the query are real, but they are a statement about questions and not the whole story. That in how many questions, in how many lesser questions can you can say, come to a conclusion. So maybe some one of the you can say person asks maybe 10 question, and the other asks maybe 50 question to get to that particular answer. So the person who is asking 10 questions is efficient, is doing the work efficiently, and this is what we are actually looking for. So the idea of phase kickback, this is the single most important mechanism today. The algorithms that we have been just starting with, okay, we will discuss Deuce algorithm, Deuce algorithm, or maybe some other types of algorithms. The idea in here is that without phase kickback, we won't be able to do anything. So please hold on to this idea that what exactly this phase kickback does, and how this trick can be used to specifically put the target qubit in the minus state, and or maybe oracle's answer they stops being a flipped bit, and uh, they become a phase instead of like instead become a phase on the input qubits. So it might seem very hazy that what exactly is this phase kickback, where it is coming from, but let's just uh, keep focusing on what exactly this phase kickback is telling us. First of all, why is this idea powerful? Because phase is precisely what interference can act on. And the oracle that we just discussed, it kicks its answer back onto the inputs as a phase pattern. That is, we turn a question about values into an interference problem. So just before this, we were discussing that, okay, we need to ask less amount of questions. But that particular idea about asking less questions, it is not just a simple idea, because it is a kind of a subjective idea. So what we are saying that we are transforming the idea of asking those questions into the idea of an interference problems. It means the oracle is kickbacking its answers, or you can say values, into the inputs as in the terms of a phase. So this is the basic idea around the phase kickback. Now, the first problem that we have is the Diush-Zosa problem, but actually the idea started with not this Diush-Zosa problem. This is like this was the one first formal algorithm, but Diush alone proposed the idea of function that is either constant or balanced in 1985, and it was just for a single bit, a single input, one bit input, and it was a very basic, you can say, problem. Whereas this Diush-Josa problem, that is Davis Diush and Michael Josa, came together to formulate, to generalize the idea that Diush has had discussed earlier, that whether a function is constant or balanced, into an n-bit function, or you can say n-bit problem. And what's the idea around, first of all, the Diush algorithm is that the mapping, let me write in here itself so that you can understand. So the mapping of problem is like this, that we have one function fx such that the input is like 0 1, and output is also like is 0 1. So this is guaranteed to be either constant or balanced. This is what the idea starts with, that is the Diush algorithm. It is not Diush-Josa, it is Diush algorithm. The idea of having the input as one bit and the output is also uh, uh, coming out to be one bit output. So in here, what we see in this particular sense is, classically we will need two function calls to get the idea that whether uh, we are how we are able to evaluate the function. So what exactly we do in this regards is we prepare the inputs simultaneously using superposition. That's the uh, idea. That's the quantum idea. And when we prepare both the inputs, that is 0, 1, simultaneously, we then move towards the oracle. And this oracle is going to evaluate both of them, that is 0 and 1 at once. And after interference, a single measurement will tell whether the function is constant or whether it is balanced. So this is with respect to the idea of how a quantum idea will uh, give us the solution in only one query. It is giving us answer in one query. Whereas the classical idea, it needs two queries. And why so? Because we will need to evaluate F0 as well as F1. And this is why the two function calls are required. So this is the idea, this basic when I have written with the marker is the idea of Deuce algorithm. So Deuce Josa focused on generalizing this problem, and they came up with the idea of n-bit input. We have two you can say bits, that is 0 0, and with respect to two-bit input we have 0 0 0 1, four outputs, and 1 1. So what will be the idea in here, that this function will be constant only when the outputs all outputs are identical. So the idea in here is that the function will resolute to a balanced understanding if exactly half of the idea is half of the inputs are 0 and half of them are 1, and the constant will be when all the outputs are identical. So if we take an example of n equals to 2, that is just as we are taking, in the case of constant, what will be done, that all of these values will need to be 1. Then only we can say that this value is constant, or this function is constant. This we say constant. Whereas in the case of balanced, what will be done, that when 0 0 and let us say 0 1, we just use this eraser, 0 0 and 0 1, they are actually equal to 0, coming out to be 0 just after measurement and all, and 1 0 and 1 1, they come out to be 1. Then we say that this function is what? It is balanced. So this is what the idea around this Deuce-Joseph problem. And to do so, to do this particular, to get this understanding, I hope everyone is now seeing this classical worst case that it will take, that is 2 raised to power n minus 1 plus 1 evaluations, that is half plus more than one more than that. We need at least these much evaluations for uh, understanding whether the function is constant or it is balanced. And this is the in worst case. Whereas what we are saying that one example for this can be that if we have, before proceeding, if we have n equals to 10, so this will need 2 raised to power 10 minus 1, that will be 2 raised to power 9. So 512 plus 1, it is 513 evaluations. So this is what it will take. Whereas what we are saying with respect to the quantum solution is that we just need a single query with certainty. We just need a single query. And now you can understand that where is this speed up of all the discussion of speed up is going, because compare 513 evaluations just for one basic comparison. If we have n equals to 10, and in here we are saying that it will need only a single query. Let us not even just take n equals to 10. Let us, if we even take n equals to 3, then how many operations will need? So we will be needing 5 evaluations, that is 2 raised power 2 plus 1, 5 evaluations, and single query compared with that 1 versus 5. Obviously, 1 will every time will be winning in comparison to whether it is can say n equals to 3 or n equals to 5 or n equals to 10. So the idea that uh, we have with respect to this Diush-Josa, this is very, very important, that in quantum solution, we are getting this exponential advantage. And why exactly this is a kind of fair fight? Because the promise makes the answer well defined. The only thing that differs is how many questions you ask. So what was the promise? That we know, we at the start we know that what is exactly is the oracle. That is what we started with. If you see in here, we were discussing, when we were discussing the oracle model and the idea of phase kickback, we stressed upon this, that okay, we know what exactly the oracle is, although it is hard to make for some real you can say real hands-on ideas. But let us assume for these problems that are proof of concept algorithms, whether it is Diush-Josa, Bernstein-Vazirani, or Simon's algorithm, these are proof of concept algorithm. They assume that we have the idea of oracle, and we do not need to you can say go about making an oracle. So okay, if we are understanding this, then we are focused on what the number of questions that are differing from the classical case and the quantum case. This is what we are concerned with right now, with that particular assumption of knowing the oracle. Let us now see step by step that how exactly this Diush-Josa actually work. And this will also consume the idea of the Diush algorithm that we were discussing. Can I just write this? Maybe, okay, no issues. I will write at the end. Now, how Diush-Josa actually works is, it is a combination of the header that are applied onto the oracle, and again we apply the header and then we measure the our qubits. So step by step, first we will see this how theoretically, conceptually it works, and then we'll move on to the architecture of this particular Diush-Josa algorithm. So the pattern that we are seeing right now is, we will be seeing this three more times today. So when we discuss the idea of other Bernstein-Vazirani, Grover's, and Shor's algorithm, so the basic idea is same in all the algorithms. So first of all, through header marks, what we are doing, we are achieving this superposition. We apply Hadamard to all input qubits, where we try to see for 2 or 3 input qubits, so that it becomes easy to understand what exactly is happening. So for all the inputs, we will be first applying the Hadamards onto them. Then the oracle writes its answer into the phases, that is, we apply the oracle. the second part. So the answer will be written into phases through this idea of phase kickback that we discussed earlier. We are not going into the deep details of the mathematical details of phase kickback. It is just the idea that you need to understand that the phases are passed on the kickback onto the starting point through this phase kickback mechanism, and the oracle harnesses that idea. Then third step that we see that the second layer of Hadamard's, this one, that is the second layer of Hadamard's, is making those phases interfere with each other. And uh, what exactly this comes out to be is very beautifully simple. It will mean that all zeros lead us to a constant you can say function, and any other outcome other than all zeros will lead us to some you can say balanced outcome. Now, one important idea in here, we are saying all zeros outcomes. So if we get 0 0, then this is constant, and other than that 0 1 1 0 and 1 1, this actually gives us a balanced function. Keep this in mind, because this is important to understand. When we earlier said that all outputs are identical, this is what we mean from that particular context. It should be given some more context that all outcomes will be identical, but those are all zero outcomes. Whereas the outcomes other than these 0 0, if we get anything for this two bit input, we will be getting a balanced function. And the same happens with a 3-bit input, or more than that, n-bit input. So all of this is decided in just one quick shot. So this is what the idea around Diush-Zosa algorithm is. Also, the intuition around this algorithm is that for a constant function, every path is reinforcing at all zeros outcome. Whereas of balanced function, they cancel themselves completely. So a single non-zero bit gives it away. And this problem is itself a very small toy problem, but the principle, that is the interference reading a good global property of a function, is exactly what uh, powers everything that follows. So this was the first clear provable quantum advantage that was established in 1989 with this algorithm. Although Dush algorithm also gives us some basic idea of an advantage, that is, instead of two classical queries, we need to just use one uh, query in the quantum solution. But that was not a very big, you can say, exponential advantage. So when we uh, discuss about a good, you can say, idea of exponential advantage, this is the first algorithm that comes to our mind. Now, let us go back, sharing my screen again, and we'll try to see the Diush-Joseph algorithm. Yeah, this is the algorithm. Now, in here, if you see the idea uh, around Diush-Joseph, what exactly is happening is we are taking uh, 3 bits, and if you see the stacks in here, that we are having the 8 outputs in here with respect to that, the 8 values with respect to the amplitudes. And what exactly are we doing in here practically? That we start with the Hadamard's in all the qubits, this is actually two qubit, because in the last we are changing the had the value to, first of all, the state is one, and then we are applying the header mart. So this will be just giving us the solution. That is known as kind of a auxiliary or an auxiliary qubit that stores the answer. So this is just a two qubit example. And what exactly we are doing in here, that we apply the header mart to the first qubit, and again applying header mart to the second qubit. As discussed, we were discussing the same thing, that first we apply the header marts in all the qubits. Then after applying the header marts, this last qubit will be first of all changed, that is the state will be changed so as to preserve the answer, that the output that will be coming at the last. And this is a barrier, this is nothing else, just a barrier. It is to you can say make changes in these specific parts. That we, first of all, this is the, sorry, this is the header marks, this is the oracle function that we were discussing, the oracle. This is the next set of header marks, and then we measure that. And this is what exactly is written here: header marks, then oracle, then header marks, and then measure. So the barrier just keeps out the distinction of what exactly is a particular idea in here. So first of all, we are creating the superposition with this two all the qubits. Second, the oracle. Just a second. The oracle will evaluate every input simultaneously, and if you see closely, the first C naught, that is the C naught gate, is connected with the first qubit, that is this particular qubit, and the second one is the second C naught is connected with this qubit, and this is, there is no C naught for this third one, because this is an auxiliary qubit just for storing. This is not actually being you can say being used in the computation. Then we again have the barrier, and we apply the header mart, and as you might remember, that when we apply header mart one time and the second time again, it will result, it will go back to its original state. So what exactly we are trying to harness from in here is whatever the operation that this oracle has performed, this particular C naught gates in here specifically, we will be able to see those answers after applying this header mart again, so as to reverse the state. And then lastly, we apply this measurement. So this measurement is from this for the first qubit and for the second qubit, and this when we measure this, this is actually giving us the two basis states, that is 011 and 111. And what exactly this solution is, this is a balanced solution, because if you read this out, what we are getting are 01 and 11 state. If we would have been getting a 000 in this particular context, we would have said that okay, this is a you can say a balance, or sorry, a constant function. So this is the idea around having a running a Deutsch Josa algorithm. So how we can get a constant function? There you need to just do some turnaround with this circuit only. There needs to some changes done that in and it also depends that the constant function, what exactly is the constant function, whether it is fx is equals to 0 or fx is equals to 1. That is the starting idea. And uh, let me show this again. Coming back to here. So what exactly we mean, that as we said that fx equals to 0 or fx equals to 1, with this starting point, our circuit will change. If fx is equals to 0, then we will be just removing the barriers, these barriers, and with those we do not have to do anything else. We just remove the barriers, and this will result in our function moving towards the constant state. Let us try to do that. Maybe we can replicate this whole setup and open it in another IBM quantum composer. We'll try to see whether it is performing or not, because it depends on system to system. Just a second. No. So first of all, let us put it as 3, 3. I'm thinking that it is not. Okay, 1 second. Let us take this again. Okay, it is not coming. No issues. Let us quickly put this. Take that much time. Then what we have, the C naughts. Another C naught. Then Hadamard. Then Hadamard. And then we measure, do the measurement. Okay. And then we again do the measurement. If you see, we are getting another kind of a balanced function. It is still doing a kind of a balanced function. So no change is there with respect to if we are just removing the barriers. Okay, so if we see the function in here, if you understand by this, it might seem in this, it might seem that okay, when we are actually measuring first and then applying the header mark, but this is not the case. If you see in the code, this HQ0, that is this one, is applied first, then HQ1 is applied, and then we are measuring. This is because of the placement that happens in the IBM platform. So it is dependent on the platform that how it is actually being done. So this is not any kind of problem. This is showing us the same kind of a result, nothing else. So I hope everyone is has understood the idea of what exactly goes on behind the scenes in Dush-Zosa algorithm. Are there any questions till this point? Let me know quickly. Have you understood it? Is there any problem with the idea and with the understanding? No? Is everyone understanding this? Because this is the you can say the simplest algorithm that we have just discussed. After this, the next 3 days, or you can say the next 2 days, we will be just building onto this, and it will become complex and complex, more complex. Okay, if there are no questions, let us move forward and discuss the other algorithms. Okay, so next we have the idea of Bernstein-Vazirani. Now, what exactly is this algorithm, the Bernstein-Vazirani algorithm? So, with the start point of the Deuce-Joseph algorithm, this algorithm is has some small twist that is like genuinely striking. And what exactly we start with is there is a hidden bit string in here. we have a hidden bit string in one query, and the function is returning its dot product with the input. So we are returning the bitwise dot product with this hidden n bit string, and our focus is to recover this x, recover this s, and classically we extract it one bit at a time. And when we extract it one bit at a time, we might need n queries for n bits. It's a kind of a game, like a guessing game where we are trying to guess a password character by character. This is the idea when we do it classically. Whereas in from a quantum setup, what we say that we will only need one query to recover all these n bits at once. And the machinery that we have is the same as the Deuce-Joseph algorithm, but now the interference is it hands back the whole hidden structure at once. That's the difference in here. What exactly is being done? That it is giving us the interference is returning the whole hidden string at once, not just one bit of information. That was being done in Deuce-Joseph algorithm. So we were getting 00 or 01 or 10 or 11 with respect to 2-bit idea. And in here, we will get this whole string, that is a whole hidden string, that is this S in one go itself. Now, what's the pattern? What's the idea in here? It has the same skeleton. That is, we start with the header mart, then we apply the oracle, then again we have the header marts, and it will be then measured. So this idea of Bernstein-Vazirani as well as the Deuce-Joseph algorithm, these are just the basic, as I iterated earlier also, that these are just proof of concept algorithm, that these are just toy set of problems. So the basic understanding, the basic structure in both remains the same. And there is also one more algorithm that's a kind of a made up problem, that is known as the Simon's algorithm, that we are not discussing, but yeah, the basic idea remains same. So that is why we are excluding it. It runs on the same pattern, that we have to find some bit string, and ultimately we need to solve some, let's say, linear system of equations. And linear system of equations requires some classical, you can say, interpretation, classical solving. So in here, again, what we are doing, that the oracle is encoding the secret string, that is the S, into phases, and this is done using the first header marks, and uh, the header marks at the last, the final header marks, will convert those phases straight back into bits that we can read. And this is measured once, and as soon as we measure it, the secret string, it falls out deterministically. So this algorithm is like the cleanest, or this theorem is like the cleanest example of how phase kickback actually recurs the hidden structure. And it's precisely the idea that the Shor's algorithm uses to scale up uh, to recover a hidden period. So this Bernstein-Vazirani algorithm is pivotal because it is being the basic structure is being used by the Shor's algorithm to find some pattern, some hidden period, and this hidden period will be actually used in the order finding idea of Shor's algorithm that we will be discussing later in today. And that is the whole transition in here, that the Deuce Josa and Bernstein Vazirani, they prove the engine on toy problems, and then the Grover and Shore point it at problems that we actually care about. So this is the basic transition mechanism. Let us now again go towards the second of, yeah, this is the structure. Uh, so this is structure is of Bernstein Vazirani, and what exactly is happening in here. This is a 3-bit problem. Again, as we discussed, that this is an auxiliary qubit, so it will not be contributing. It will be just storing the value. If you see the structure, it is somewhat similar. You see, we have the Hadamard's, and the last one is the we can say the flipped a bit, and we apply the C knots, and again we apply the Hadamard's to get the result, to get the phase back. And this is again the same thing, but there is a difference. It's simple difference, a very small difference, that the first qubit is the control bit, and the last one is the target bit for first C naught. But the second C naught is giving us is having the third qubit as the control bit, and the last one as the target bit. So this is actually a little bit difference of how this oracle, this particular idea, that is the C naught gate, how it is being how it is being used in different manner. If in case I change this oracle to have like pointing the control bit from the second qubit and the target bit at the last qubit, then it will change the progression of what exactly we are actually getting. That is, we are right now getting 1101, or you can it means the secret string is what 110, because last one is not our of our use, because when we measure this, that is, if you see, we measure the first qubit, second qubit, and third qubit. Fourth qubit is as it is, so that is why we say that 110, it is like that. Now if we change this pattern, let us try to see that what exactly this tells us. We are moving this control from Q2 to Q1. Now, if you see, we are getting some another state, that is 1011, and this goes on for different patterns, interference patterns, that we change. If we again apply this as like this, we are getting this 1000. And how is this actually coming up is just the basic understanding of mathematical operation. It is nothing else. We apply 3 Hadamard's in a joint simultaneously. That is, we will be doing some tensor products. With this tensor product will then on this tensor product will we will be then applying this C naught gates, just as we applied them for the idea of entanglement. And then these you can say the C naught gates, whether we are using this pattern or this pattern or whatever pattern, this C naught gates will be applied to get you can say matrix that can be then again utilized with by applying the Hadamard gates, and this will result in actually getting us to this particular state, that is 1101. This is the whole idea around mathematically around this Bernstein Vazirani algorithm. Okay, so next we have the Grover's search algorithm. Let's put that as, yeah. Now, Grover's search algorithm tells us the idea is this is the kind of a first algorithm that somewhat feels useful. Till this point, we were just playing around. We were just playing. Okay, this we can do this, we can do that. A random, as you can say, uh, assignment problems that just we have. We were doing something like that. But this Grover's search algorithm, it solves a very critical fundamental problem that we have currently. And what's that problem? That imagine an unstructured list. We have an unstructured list. What we have to do is we do not have any sorting idea, and we do not have any pattern, and we need just one marked item. Let us take just quickly 1, 4, 5, 9, 10, 3, 6, -1, 0, 8. We have something like this. I've taken too many items, but yeah, let us say that we have something like this, unstructured list. If we want this 3, we want to find this 3. What exactly we need to do? Classically, we have no choice but to check them one by one. And on an average, we might need to check only half the list. This is the idea with classical computing. And in the worst case, we will need the whole. We need to check the whole this list. So we will need an time. But the idea of Grover that he discussed, he you can say invented, it needs only a square root of n queries. So if we have a million items, that is, we have some 10 lakh items, we won't need to check for either 500 classical checks, that is on average, or the full 10 lakh items. Instead, we will only need to check for 1,000 quantum steps, approximately. This is what the Grover's search problem gives us the advantage. And why exactly is this important? I hope everyone is understanding this, that the handling the unstructured list, whether it is present everywhere in the whole in any work we do. So even if we are just finding a simple file in our computing system, it is using some unstructured, you can say, it is finding something in some unstructured way, and we have to it takes a little bit of quite a bit of time when the file is maybe like 5 or 10 year old, and because it will go one by one finding the files. So this idea is actually very uh, useful at the Grover's algorithm, uh, because unlike till this point, unlike our toy problems, this is a kind of a shape that's everywhere. Whether it is kind of a searching idea, whether we are doing some brute force, applying some brute force technique, or we need to do some constraint satisfaction problem, handle constraint satisfaction problem. So this is one of the most, you can say, genuine idea that is uh, powering everyday, you can say, problems. And this is how this actually works, because we have understood, okay, we will need only 1,000 steps, but how exactly this works, this is why where the idea of this interference comes in so handy, the understanding of what exactly goes behind the scenes. So we have this idea of amplitude amplification. This is what we say, that you amplify those amplitudes that are correct, and you suppress those amplitudes that are not correct, that are not you can say correct to your liking. So this actually makes the interference visible, and it's worth slowing down, that we need to understand this step by step, that what exactly is happening with the right from the start. Although in comparison, Shor's algorithm gives us an exponential advantage, speed up, instead of just quadratic speed up as Grover's is giving us. But this idea of Grover's search is much more, much profound, and it has been uh, uh, quite applicable to many problems, as I was discussing about max cut or any problem like that, and other problems also. So the idea of this Grover's search algorithm is actually very powerful. So we first of all start with the having the idea of having the probability, or you can say every item is equally likely at the start. That is the idea of equal superposition. So we are starting with equal superposition over all n items, and every amplitude is equal to 1 by root n, right? That's the starting point. Uh, then we need to repeat two specific moves. First of all is the flipping of the oracle, that oracle flips the sign of the marked item's amplitude. And secondly, the idea of this diffusion operator. Diffusion operator actually reflects everything about the average. So what exactly is happening with respect to this oracle and diffusion operator is that uh, we mark down those amplitudes, or those items that are like correct, and uh, we do not and we unmark those that are incorrect. But here's a very specific question that uh, came in my mind a little back, some time back. I was perplexed by the idea, and I asked. I tried to find it many places, including some Gen AI tools like ChatGPT and Claude and others. That how are we at the start knowing that this is marked, and or you can say this is the correct solution and this is the incorrect solution. That this problem, this idea. Came to my mind in some time back. So I was perplexed that how are we stating that this is correct and this is wrong? Because if we know the correct answer, why exactly are we doing this search? Because we know the correct answer, we have to just fetch it. We can fetch it quickly. But when we have to find that, okay, where exactly is this correct answer? That is what is actually consuming some energy. Um, so the problem, the idea lies in this, that when I tried to find the answer to this is with respect to the idea of oracle only. That is oracle, that is a black box function, and how we build this oracle, how we uh, you can say try to establish this oracle through different ways, through different mechanism. This is where the understanding of whether this a particular item will be marked on unmarked, it is actually residing with this oracle only. And this is why we at the start we discussed that it is not just about having the less number of queries. It is about understanding that how an oracle can be built. Because if we are not understanding that what exactly is happening inside an oracle, we are just you can say kind of discussing at surface level. We are not deep diving into what goes down, what exactly is happening inside this black box. So for now, the answer to this question uh, that invoked this idea that I kept thinking that how am I marking the items as correct or incorrect right from the start, even when I am not knowing even the answer. So this actually lies with the idea of how the oracles are developed. And right now we are not going into the deep dives of how to build an oracle, because that it itself is very tedious. We can say it is very tough or hard problem to handle. But the understanding is that everything is being governed by this oracle. And what exactly is this oracle? That also needs to be understood, that what exactly is oracle in perspective, that what is inside this oracle. So to understand that, we say that the oracle consists of some functions only. It's a kind of a reversible quantum circuit. The oracle is an reversible quantum circuit, and not just a magical, you can say, black box. It is implementing, that oracle is implementing a classical function using some unitary operations. And the unitary operations that we discussed, that the gates and all, that is what is actually coming to the fore. So the basic understanding of an oracle is something like, let me write in here so that you can understand this. This is very basic. It is generally used in the Bernstein Vazirani and uh, you can say Dish algorithm, but this is the basic operation. Typically, we use this for oracle, that is UF, that is unitary function. This get x, y, that is XOR of fx. So this is how we just write a simple oracle. And temporary values, that is the garbage values, are removed using uncomputation. And we restore the ancilla or the auxiliary qubits, as we were discussing, and ancilla qubits to their initial state. So algorithms like Grover's algorithm, they use a phase oracle. They use a phase oracle. And what exactly this does is, it will use phase kickback technique to mark solutions by changing the sign of their amplitudes rather than storing the output explicitly. It is not storing the output that, okay, if we have to find this 3 value, the value 3, it is not storing this particular value. It will be just changing the sign of the amplitude with respect to 3. So 3 is just a value in it, but the amplitude associated with 3, if we are seeing us taking writing it like this, let us say that the amplitude will be like this: alpha 1 2, alpha 2 1, alpha 3 4, alpha 4 5, alpha 5 9, alpha 10. It is like this: alpha 1 2 plus 2, 1 plus alpha 3, 4, and so on. So when this is done, what exactly is being done in the terms of phase oracle that is being used by Grover search? It is just changing sign of their amplitudes, that is these alphas, is change the sign of these amplitudes, than storing the output, that is the value, explicitly. And this enables later interference to amplify, that is done using the diffusion operator. It will amplify, and this amplification will actually give the probability of measuring that particular entire desired state. So this is what exactly goes on in the background about the Grover's search algorithm. Okay, so I hope everyone is understanding the basic idea uh, of what exactly happens with respect to this Grover's search algorithm, because this is the most important, very, very profound idea, very important idea. And uh, if you are able to understand this, you will be like uh, able to understand the ideas around how what different problems can be solved this Grover search. That is, we have just started. We started with the basic idea that the search problem or the brute force techniques, and any problem or constraint satisfaction problem. So these how these problems can be modeled using Grover's search algorithm. Now, uh, before moving towards the idea of this caveat, let us go back and see the idea of a Grover search algorithm. Just a second. Keep it. So this is the uh, yeah. See this. Now this is a structure that we have uh, for a Grover's search problem, and right now it is somewhat very highly populated. We are just seeing 2-bit example, uh, and this is like inspired from the one of the major I have seen explored platform, that is Qniverse. This is a government platform that is CDAC has developed it, and you can explore. I hope it is visible to everyone. You can explore the different algorithms in here, and you will get the circuits that we are using. They are attributed to this Universe platform in only, and you can see the whole we can say the composer, just like we have the IBM composer in here, but it does not charge any credit or anything else. We can freely do it. This Universe platform actually uses some credits, 5 credits, with basic credits to just simulate the problem, not nothing else. It's not taking any money from you, but it's just does some you can say, see this, we can use different backends, whether we want to use on a CPU or a GPU. So it takes a little bit credits to run this problem. So I try to imitate it on the IBM quantum platform. And as you can see, what exactly is happening in here, if you see from the code also, very basic idea, nothing problematic. These are just gates, nothing else. We start with the Hadamard gates. We start with the Hadamard gates, and then we are applying the idea of this negation, that is a NOT gate and the Hadamard gate, and from there the idea of oracle comes in. This is the oracle that we have, and this oracle is actually implementing something inside the some changes are being done inside it, and because of which we came to the conclusion that okay, our marked state is what 10 actually and nothing else. And if you see the phase angle, it is pi. And why exactly is this coming as pi? If you understand the basic equation from junior level mathematics, that we how do we see those equations? Cos theta plus I sine theta in that sense. So the phase angle, how it is changing theta, that how it is actually giving us the value -1. So cos pi and sine pi, how we see that, this is what it is coming out to be. So cos pi is like -1 and sine pi is 0. So the value that is coming out to be is -1. If we change the arrangement somewhat, we are not going to do that. It will like do a drastic change in here. If we change some parts of here and there, we might get some other state other than 10, as this is a just 2-qubit state. So we are getting the state 10, and we can get another 3 states. But the idea in here is we are seeing the state that is 10 with that particular idea of having this oracle flipping the sign, as well as it is reflecting all the amplitudes about their average. Although we are not able to see the average in here because this is the state vector only and not we can say a value that we will we can explicitly see. But the idea that moves around it is that we are able to see this particular you can say sign flipping, and this sign flipped sign is actually telling us that our marked state was 10, and this is what we actually are getting, and this is the correct solution for us. So this is the idea around Grover's algorithm. Now moving to the idea of how this actually runs through the Python programming is, first of all, we have you can say some ideas around how superposition is done over all inputs. This is a general idea, and the phase kickback idea, that is how phase kickback is used to run the idea of the Deuce-Joseph, Bernstein-Vazirani, and Grover algorithm, and then how we can do build the Deuce-Joseph algorithm with the 2 oracle types, that is 2 different oracles, fx equals to 0 or fx equals to 1, and uh, if we decide to go for constant or balanced, how we can get that, and the idea of Bernstein-Vazirani as well as the idea of Grover-Selch algorithm. So let us first explore these algorithms, and then we'll move towards our next, the last algorithm for today, that is the Shor's algorithm. It is very, very important and a very uh, uh, interesting algorithm. Just a quick idea in here, that the idea around the Grover's algorithm is that the generally we think that if we have more iterations, it will be actually beneficial in the long run, but that is not the case with Grover's algorithm. It's not necessary that if we have you can say more iterations, then it will be beneficial for us. So the marked amplitude, as we are seeing specifically, it rises, then it peaks near this these number of iterations. So whatever n we have, that is perfectly okay, but it will peak around these number of iterations, and this is where the whole idea of the rotation overshooting its target is coming from. So the understanding is that you must stop this stop around this optimal point, optimal count, and running it longer will actually lead to some less, you can say, success. And the idea is that this algorithm is giving quadratic speed up, not an exponential speed up. So that is okay in one terms. If we compare it to Shore's algorithm, it might seem that okay, we are getting less speed up, but uh, the vast range of problems that it can cover, Shore is not able to, like right now, Shore is not able to, Shore's algorithm is not seen as that problem that can cover a kind of a vast range of such problems, brute force problems, or whatever problems we see in practice. So the idea blooms around the contrast with the classical, you can search, where we understand that the extra, you can say, checks, they never hurt, but we need to be clear on its scope, that this is a quadratic speed up, as we have been iterating this again and again, and not exponential. So it applies so broadly that it matters very, you can say, in an enormous manner. Okay, let us now see these codes. First of all, what exactly is happening one by one, and then we'll move to the last part for the day, that is the Shore's algorithm. We'll see that quickly, and what's the understanding behind the Shore's algorithm and the impact of Shore's algorithm on the cryptography. And this saying that I had discussed on the first day itself, harvest now, decrypt later, very important idea, and how this can be used for this post-quantum cryptography understanding. Okay, let us discuss this course. Now, this is the setup. This needs to be done every time you start with. We do not need to go about this every time. It's just the all the libraries that need to be we need to start with. Now, first idea that we are seeing in this particular setup is, it is telling us that how uh, we apply superposition over all inputs. And this is the same idea that we were just seeing, that we apply first of all the header marks on all the qubits, on the all the inputs, sorry. So if we have three, you can say, inputs, we are just applying the header mark onto it, and it will be equally weighted inputs, and that is 0.125, 0.125. It will be giving all weighted inputs for that. So a quick note onto that. If I just this. Just a second. I want to show that if we are applying this, if you see this, let us take it as 3 only, so that we do it. So if you see this, everyone is getting 0.125, or the 12.5% of share, that what we were discussing. And if you want to see the state vector also, that's the same. It is 0.354, 0.354. Why it is, this is amplitude, this is not probability. So probability will be 0.125, but the amplitude will be with respect to what? The value that when we square it, and what exactly this value is coming out to be. So when we square all this, it will be coming out to be 1 only. So this is the basic idea with uh, the first understanding of what goes around superposition over all inputs. Then the second idea, that is the phase kickback. Very important that we started with. What exactly is this phase kickback? How this can be run? We need uh, 2 qubits and one, I can say, classical bit. So let's try to make that like this, and we just remove this one. Now, what exactly is happening with this circuitry is that on the first uh, bit, we are just making the target bit, and the second, this one, the H0 is the control bit, and uh, the oracle is actually coming, the idea of oracle is coming from this C naught gate that we are using, and it is affecting this kickback onto the control as phase. That is, the control, you can say, qubit is kicked back as in the terms of phase. Although, what's the idea? Although generally the phase that comes up is with respect to the control qubit, but when we kick back this particular phase onto the control, this is the change that actually comes in. So if we try to imitate the circuit, what exactly we are trying to show in here, that control will be flipped to 1 by kickback. Generally what happens when we see the control and the target qubit, if you remember from yesterday, we saw the idea that when control is 0, target will be 0. If it is will remain intact. If control is 0, target is also 0. So we will be getting 0 0 itself. But if we have control as 0 and target as control as 1 and target is 0 or 1, the target qubit will change, whether depending on whether it is 0 or 1. So with 1 0, that is controlled 1 and target 0, we will be getting 1 1 as our output, and with 1 1, that is controlled 1 and target 1, we will be getting 1 0 as our output. But what is happening instead here, that we are putting the target in minus state first of all, and then the oracle's answer is coming back as a phase onto that particular control. Let us try to imitate this. First of all, let us try to see this. So move this. We are just using this first. If you see this, we are just applying the x1, that is 2 1, and add a mod in here. That's what is being done in here. If you see qc.h1, also we are applying header mod in here, and then we apply this C naught from 0 to 1. C naught is applied. Then we apply the header mod onto 0 again, and then we measure the 0 0. Now, what exactly is this measurement telling us? Yeah, sorry, this should not be there. This is not measurement. Now, if you see in here, what exactly is this giving us in the terms of idea, that we are getting a change in the terms of this 0 1 when we change it from here. Yeah, see this. That is, the values are now getting kicked back in the terms that this value, that is the second, this 1 1 is coming back as minus 0.707. That is this amplitude. The phase angle, if you see, this is 2 pi. So it is doing a full circle, as we were saying, that the whole rotation, and this one is doing not the full circle, it is just doing the 180-degree circle. So this is what the idea is coming with respect to the idea of phase kickback. So I hope everyone is understanding this idea, what exactly is this phase kickback is actually giving you. Now in here, again, same problem, the problem of little endian and big endian. So that is why we are relying on this particular understanding. It means we will be seeing this 1000 times. This is what we are getting, although the results in here are different, but in the terms of probability, if you see, this is what we are getting. This one is getting 1000 times. So this is not a problem. This is just the measurement, and this measurement will actually be giving us the value. Now moving towards the Deuce-Joseph algorithm. So what this Deuce-Joseph algorithm is, we discussed about the constant and the balanced functions, and these constant and balanced functions, how they actually are made first of all. So we have used this quantum circuit for n plus 1, you can say, qubits. What this n plus 1 means, we are just using this particular function that is coming from Python itself, from the library, that dj slash underscore oracle. And what this means is that we have n input qubits, n plus 1, and one output qubit. And this is the same thing that has been implemented in here. That is n input qubits and one output qubit. So this will be like a auxiliary or ancilla qubit that will be just printing out the output for us. And we are applying the value that if the kind is that the function is of constant type, then do some certain task. If it is of balanced type, that is then do this particular task. And this function is being used in here indirectly to come to the conclusion whether the function is constant or balanced. So how it is coming out to be constant or balanced. And this is, if you see step by step, we started with the same idea, that is n plus 1 comma n, that is the kind that we are seeing. And we apply the Hadamard's to everyone. That is what is being done in here. If you see this line, particular line, that is Hadamard is applying to all the range, all the n plus 1. And before that, x is applied to the last one, that is this last qubit, this qubit. And we are applying Hadamard to it also, that is this last one. Then we are composing this dj underscore oracle. And where is this coming from? This is coming from this particular this whole function is being used. And this function is harnessing the idea of how whether the function is constant or balanced. So when we find the kind, whether it is constant or balanced, based on that we will be giving us it will be giving us the output. If they are all zeros, it will if we are getting zeros every time, 1,000 times, so for the 1,000 sorts we are getting 1,000 values, it means it is constant. Else, if we are getting any other solution other than 000 for 3 qubits, that is we are getting 110 or 011 or 010 or 100, we will say that it is a balanced function. So this is what the idea is around Deuce-Joseph. Then we have the Bernstein-Vazirani, and Bernstein-Vazirani focused on what? The string, that is particular string. What was that? That S, that how we can find this hidden string. We do not know from the start. So what exactly we used, that we start with a particular, you can say, a random assignment of a string, and this secret string, as it is taken as 1011, because we are assuming that we know the oracle. So we are putting up this 1011, and we will be checking this x s dot x mod 2. That is, we will be checking these operations every time for new inputs that we get, that is x. We at this 1011 will be dot product with this particular x mod 2, and whichever is string this input will give us the correct solution. It will be or you can say it will be giving us the correct solution. And as we change the secret string, we can confirm that how the measurement is actually tracing back. So if we change 1011 to 1110, it will give us some different type of answers. So this is what it is coming out to be. Then very important issue with respect to the Grover search, the idea of amplifying the marked item. So how it is done? It is focused on using the idea of phase flips. And these phase flips are, if you see, first of all, we use a Grover oracle, as discussed earlier in the slides also, that we are using the oracle and then the diffusion operator. So oracle will be focusing on this marking of the items, marking the items amplitude. That is what is being done in here. We are marking with respect to the CZ. We are using Control Z gate, so we can do some phase flipping, and this phase flipping is actually, this phase is actually the marking. We are not just going and doing using some marker and doing some marking out there some item. It's the idea that uh, instead of uh, keeping a note of how many queries have been done, we are actually shaping it to how you can say how it can be marked using phase. Then the idea of diffuser. So diffuser is actually focused on doing reflecting the amplitudes, and these amplitudes are reflected about their average. So this is what the diffuser is actually doing. And uh, in here there are many ways to implement Grover's algorithm, many different ways. Uh, the main understanding is that you can implement in any so way. Just like we, as I uh, uh, dis, conveyed earlier, that I am using this way of applying the Grover's algorithm, and we are getting the result, intended result. And this is coming from the this particular documentation that we have for from the Quniverse. So uh, there is no you can say just kind of a unique pattern that okay, you have to have this unique pattern only, and then only Grover search will work. It is not like that. There are different ways to go about it. And uh, uh, the main understanding is that you have to perform these two particular steps, that is marking the amplitudes, and then flipping them around with respect to their average. This is what the idea is all around with respect to this Grover search algorithm. And this is giving us the the you can say the solution with respect to this one, that is one was marked, and it is coming out to be every time, that is 1,000 times. So this is the idea around this particular you can say code. So we have marked one in here, if you see this specifically, and this has been marked, and this has been amplified. We go into equal superposition, mark one, and then amplification is done, and this is why this one dominates. We run it for one iteration only, and the number of values were 4 total. So this is the idea around Grover's search algorithm. Now the last one, that is uh, even if we are doing over rotations, that is the understanding in Grover search algorithm, that is if we do more iterations, it will not actually yield us the intended result every time. So if you see, we do 0 iterations, we were getting the 111, the probability was 0.12. If we did one iteration, the probability increased, it jumped rapidly, it goes to 0.78. For 2 iterations, we get the probability 0.94. And this was the like the tipping point of this particular you can say uh, uh, algorithm, that it is peaking now near 2 iterations. And you can check it. How you can check it? That is n equals to 8. When you put this in here, that is pi by 4 into 8 iterations, whatever number of iterations it will be coming out to be, this is where we say that this is the peak value. If we are going more than or beyond that, you are seeing the result in here, that in 3 iterations it is now fall down to 0.34 probability, and 4 iterations it is like going down way beyond. It is 0.01. So five, after 5, if we do 5 iteration, it will be like uh, just vanishing. So what's the idea around this understanding is that we need to focus on the optimal solution in here, and this is the same understanding that we have to get the idea of how optimization is actually performed. And uh, running it longer will not actually be like cutting the chase. Okay. And lastly, we can like read our results. How we can read the results? This is what the basic idea is, that if we have all zeros, it is constant, or else it is balanced in uh, Bernstein-Vazirani, we have one sharp peak, that is the secret value that will be getting as deterministic. In the Grover, a dominant peak is seen at the Marked item. That is, it is probabilistic. It is different because uh, it depends on with the number of shots. So we sharpen it with more shots. And the idea that again, this I will remind this again and again. This kit is written in Indian, so we need to have understanding the rightmost bit is qubit zero. Okay, let us move on to the last algorithm for today, and this is the another very famous, very interesting algorithm, the Shor's algorithm. Now, what happens with respect to the Shor's algorithm is that the it is the kind of a headline result of the entire field. If we want to factor a large number into its primes, it seems very easy to factor 15. Yes, we can write this. Wow, this is so simple. This we are able to do this. Very good. But what if I we are given some random number, some random 10-digit number? Now, how are we going to factor it? We are given some 10-digit random number and we want to find some prime factors of it. How are we going to do that? It's not easy. It's a very tedious problem in classical computing. Classically, the best methods that are we know are super polynomial. That is, they are sub-exponential. So a 2048-bit number is currently infeasible on any existing computer. Just 2048-bit number. So what exactly is being done in here is that Shor is doing this, the quantum solution that Peter Shor came up with. He proposed that it can be done in polynomial time. And as you compare this, that sub-exponential and the polynomial, we say it is kind of an exponential speed up over the best known classical algorithms. And notice that this idea of Shor's algorithm is different from the other algorithms that we have seen till this point. The Deuce-Josa, Bernstein-Vazirani, and Grover's that they give a kind of a query model results where Shor is focusing on a concrete economically critical problem. And what is this economically critical problem? That we are just going to see in 2 or 3 minutes, that the idea of cryptography and all. So the understanding, just a second. Yeah. Yeah. So the understanding of this quantum Fourier transform, this is where the Shor's algorithm actually gets its inspiration from. That it needs to find a hidden pattern, or you can say the hidden period. And the key, this is the key tool that is actually powering the idea of Shor's algorithm. So the quantum Fourier transform is the quantum cousin of the discrete, that are DFT. We know discrete Fourier transform, and it acts on the amplitudes. Now it is acting on amplitudes rather than just a list of number. The discrete Fourier transform, it used to act on the discrete numbers, the list of numbers that we had. Whereas this quantum Fourier transform is focusing on amplitudes, because everything in here is work around the idea of amplitudes only. So its job is to find this periodicity or the hidden structure, as we say. And how is this hidden structure is actually, where is this hidden structure? It is actually encoded in phases. Again, we go back to this same idea. We will find this hidden structure in the by understanding how to drive out the phases. And it does quite remarkably, this idea is done quite remarkably, and this is where the it is the engine of all the period finding problems. So whether it is a short algorithm or any you can say adjoining ideas around it. So the idea of encoding the phases, it is done actually in order of n squared gates or n qubits versus this the classical solution, that is n into 2 raised power n. So if you see this, this is an exponential value if we go about it, and this is a polynomial, you can say answer to solution to quantum solution to the classical, you can say uh, counterpart. So one important idea in here is that the internal working, the idea around inside the showed algorithm is whatever magic is happening is you still have to measure just one outcome at the end, and the quantum Fourier transform will simply concentrate the probability onto that informative one, that whatever the outcome we will be getting, the single output, we will be concentrating all the probabilities with respect to that result only. So yeah, so the idea of how this algorithm actually works conceptually is that first of all we find a purely classical bit of uh, you can say number theory that reduces to some period finding, that is find the period of a certain function. This is what we start with the idea. That is the reduction part. This is the reduction part. Secondly, we move towards the quantum understanding of the quantum, how the quantum core is using the idea of quantum Fourier transform to extract this period, that is coming from fx equals to a raised power x. The x is our input, the input value, that the classical bit. So QFT will be extracting that period quite efficiently using the idea of interference, and the hidden period that we are actually seeing, it will be like coming up as a sharp peak, just as we were discussing earlier, that there are some specific markings, whether it is Bernstein-Vazirani, whether it is Giuseppa, or whether it is Grover's algorithm. Every algorithm has some special markings, and with that, we actually finally that period is giving us the factors through a simple classical calculation. And what is that classical calculation? That is just defining the GCDs, and uh, by finding the this greatest common divisor, what exactly we will be focusing on, that we actually recognize the shape, and its shape is actually the value that we find through this classical computation is coming out to be the same shape as the Bernstein-Vazirani problem. And this is the same thing that we discussed, we uh, uh, focused on when we were discussing the Bernstein-Vazirani algorithm theorem, that it will be used in the Shor's algorithm. So the structure, the idea is like hidden in the terms of phases, and we let the interference read it out, and we just scale it to from a string to a period. So this is the idea with respect to the Shor's algorithm. What's the impact? Large, you can say far-reaching impact is that the idea of RSA, that is the famous algorithm that we use in cryptography, and the Diffie-Hellman exchange problem. They are secure because factoring and discrete log are hard right now. And Shore algorithm is actually breaking both. It is also breaking the idea of this how to factor and the discrete logarithm that we use. So once we get hold of a large fault tolerant quantum computer. Now, what exactly is a fault tolerant quantum computer? This is a discussion that we will be dealing quite in detail when we on day 5, that what exactly this fault tolerant and noisy intermediate scale and many things are this NISQ era that we are seeing. This is very interesting. So we will be discussing that in detail. Today we will be just seeing some basic idea. So as soon as we get the hold of a fault tolerant quantum meter, it exists, we will be able to break, or anyone who has the a fault tolerant quantum computer, they can break the RSA and the Diffie-Hellman exchange algorithm at their disposal. So today's NISQ hardware, that is noisy intermediate scale quantum, today's NISQ hardware cannot run this at scale. The the breaking the factoring and all. It needs many error corrected qubits, because as we say, it is noisy intermediate. So there is some noise present in uh, uh, the structure that we are seeing, and with a little bit of decoherence itself only, we get the qubits are they break from the superposition, and we are left with no quantum advantage. So the problem with this idea is that, as we say, that harvest now and decrypt later, what exactly can be done is that anyone can store our data today, and they can decrypt it later when they get hands on a fault tolerant quantum computer. But this is a very major problem. So the response that we are moving towards is of post quantum cryptography, that is how we can move towards building classical algorithms that are believed to be quantum resistant. And this migration is actually underway after these regulations in NIST standards, NIST standardized sets. So this we will be we can say exploring this more when we discuss about the security discussion on day 5. Okay, next we have the idea of uh, the deterministic and the probabilistic algorithms. Briefly, we'll see this. Dujosa and Bernstein-Bazirani, they are deterministic, or you can say exact algorithms, and they appear with probability 1 and same like this. But the Grover, it is very high confidence algorithm, and it is you can say probabilistic algorithm. So in Grover's, the idea of having the marked item with high probability and rerunning is a major talking point in here. And this is the understanding of the comparison between the deterministic and the probabilistic algorithmic ideas. Then we have the idea of the Shore's algorithm that succeeds with you can say good probability when we run it many times, and some of the runs will be not that good. It will be a dead rubber. But when we repeat this and we repeat until the period appears, so then we can verify it classically, which is quite cheap to check without any help. And the quantum advantage, what exactly this means is that uh, it almost never means that one run and certain answer. It is the idea that for some for the useful algorithms, uh, it will run, you can say it will do some few runs to have some high confidence. And this exactly is the way forward, because it will be saving us enormous resources in the long run. And where is the quantum helping actually? So quantum computers are not universally faster. That okay, we have one quantum computer, so it will be faster right from the get-go. It is not that. So the idea is that uh, uh, the limits are real and the class of problems that quantum computers can solve are efficient. So it contains everything that is classical computers do efficiently, plus a few extra ideas also, like factoring, quantum simulation, and many things are there. But for the everyday task, there is actually no quantum advantage whatsoever. And the problem is that we do not need to believe the myth that tries are all answer at once that we started with. We need to focus on that the quantum advantage is coming from the interference pattern and what's the probable outcome. And this is the last part. After that, we had the hands-on where we have already discussed. So the idea of Deuce-Josa algorithm, the algorithm scorecards. Deuce-Josa classically how many tries it takes. Quantum it takes one query. Speed up is exponential. It is a query understanding. Bernstein-Vazirani takes n queries. Speed up is exponential again. It is linear to constant. We are finding that. Grover's algorithm, it was taking classically n numbers and but n tries, but here it is taking root n, so it is a quadratic speed up. And Shor's, it is super polynomial in classical. It is quantum in polynomial in quantum. It is taking exponential speed up. So this is what I wanted to discuss with regards to the idea of the different quantum algorithms. If there are any question, do let me know quickly. Otherwise, we can close out the session. Thank you. Ma'am, I think we can close out the session. So please.
Yeah, sure, sir. We can wind up. Thank you. We'll meet again by tomorrow.
Thank you.